Hello, my name is Ryan Albrecht, and today I'll be presenting the paper Automatic Fingerprinting of Vulnerable BLE IoT Devices with Static UUIDs from Mobile Apps. First, I'd like to acknowledge the original authors and researchers of this paper. The authors are all from Ohio State University. They are Xiaoxun Zhou, Hangho Wen, Xinghang Lin, and Yinhuan Yang. They presented their paper at ACM SIGSAG Conference on Computer and Communication Security, CCS, November 11th to 15th, 2019 at London, United Kingdom. Below is the reference for their paper. Internet of Things IoT devices are increasingly using Bluetooth Low Energy, BLE, to communicate. This is because it demands low power consumption and is suitable for applications with small amount of data. This paper examines the security and privacy of BLE. As part of background, I will explain the workflow of the Bluetooth Low Energy protocol. First, there is the connection phase. A BLE peripheral or slave will continually broadcast its advertisement packet when it wants to establish a connection to a master. The master will be scanning for advertisements and initiate a connection request. Second, there is the pairing and bonding phase. The pairing procedure between the master and the slave will begin with the goal of creating a secure channel by negotiating an encryption key for communication. 4 pairing protocols exist: JustWorks, passkey entry, numeric comparison, and out of band. Looking at passkey entry, this is where a passkey is shown on the master device and entered on the slave device. The fact that it necessitates direct user engagement helps defend against man-in-the-middle attacks. In contrast, JustWorks has no such user interaction, making it vulnerable to man-in-the-middle. Finally, there's the communication phase, where values are written and read from the slave. It is done in a structured format known as Generic Attribute Profile, also known as GAT. Via GAT, a BLE device offers a number of services, each of which stands for a distinct attribute. As you can see in Figure 2, a BLE IoT device might consist of one or several services. In this example, there is the service heart rate, and there is also the service named battery. Each of these services might consist of one or several characteristics. In this example, the service heart rate has the characteristic heart rate measurement and the characteristic body sensor location. Finally, each characteristic might contain one or more descriptors. Central to this is the idea of a UUID, a Universal Unique Identifier. It is a 128-bit hexadecimal string that serves as a unique identifier for a particular BLE property, such as a service, characteristic, or descriptor. UUIDs are found in advertisement and data packets. In order for this communication to work, the mobile app must know the UUIDs in order to talk with the device. Having established the background, we'll go into the threat model and scope. There are 2 types of attackers: nearby attackers and remote attackers. Normally with BLE, devices can communicate with peripherals within a range of 100 meters. However, long-range Bluetooth adapters that support the sniffing of BLE extend the range up to 1,000 meters. For remote attackers, they can get malware on a device and then use this to attack IoT BLE devices. This is ignored in this paper since it's too large a scope. Looking at the types of nearby attacks, there's passive and active. Passive is where you're only listening to BLE traffic, and active is where you can connect, read, write, or manipulate BLE traffic. Under passive attacks, there's passive fingerprinting. You can get the advertisement UUIDs and then correlate this to the mobile app being used. This is especially dangerous if privacy-related IoT device is being used, like a blood monitor, pacemaker, insulin pump, etc. For passive eavesdropping, you're listening into the conversation, but this assumes that the BLE is using the JustWorks pairing method, and the BLE version is before 4.2, where Diffie-Hellman elliptical curve was introduced. This also assumes that no app-level encryption is being used. For active attacks, there's denial of service. By connecting to the peripheral as soon as the advertisement is given, other devices cannot connect to it. This is because BLE only supports a single device connection. With fingerprinting, you can get more resolution because a single UUID might be used by multiple software apps. So by using a hierarchy of characteristics and descriptors in addition to the services, you can get more UUID resolution. For active eavesdropping, you can perform man in the middle, which works for BLE greater than 4.2 and the just works pairing method. And you can also have an unauthorized device attack, where when you have used the just works pairing method and there's no authentication or buggy app level authentication present. The objective of this paper is to systematically investigate from an adversary perspective the insecure IoT devices that are attackable to a nearby attacker, and meanwhile, the various attacks that can be launched by attackers in a specific region. In order to accomplish this, they get a list of BLE IoT Android apps from the Google Play Store. They get a list of advertisement UUIDs found from passive sniffing in the area, and the result is IoT devices that are vulnerable. Towards that end, the researchers developed BLE Scope, which is a tool that encompasses their research goals. So the input is there's these Android APKs, or the mobile form of Android apps, which will be analyzed by this value set analysis that we'll go into soon. Basically doing some binary analysis to determine first the UUIDs and the hierarchy, so extracting that from the binary, as well as any app level vulnerabilities. In addition, the other input is they will be sniffing BLE advertisement UIDs in a certain region and generate a list of UIDs. And so in the combination of those, they can generate the output list of an unauthorized accessible devices. So these are devices whereby the corresponding mobile app is having some hard-coded crypto usage. And then the other list would be a sniffable devices where there's no crypto usage found. And the third list is just fingerprintable devices, so devices where you can correspond that to a specific mobile app. The researchers ran into some trouble with implementing BLE Scope, specifically with UUID extraction. While some 128-bit hexadecimal strings appear in the binary, see the decompiled code below, that's not always the case. Sometimes they can be actually generated from complex operations such as string manipulation and arithmetic. Another challenge they ran into with the UUID hierarchy reconstruction, since there's really no defining or governing rule about the structure of the hierarchy that you can just determine from the code. Thirdly, there's the flawed authentication identification. There's not really an established coding pattern for implementing authentication, and we can't really use any documented API to locate them and retrieve the hard-coded credentials. The researchers were able to solve their first problem of resolving UUIDs via context and value set analysis. Specifically, they were able to use 7 published APIs from the Android BLE framework, which took UUIDs as parameters and then traced back to constant values. This was done using program slicing and value set analysis. As you can see below, there's strings given for the UUIDs, and they are passed into functions like getCharacteristic or getService. So you could basically trace back if these aren't constant values, in this case, and then figure out what the actual value is. The second problem the researchers had to solve was the reconstructing of the UUID hierarchy. This was done with control dependency. To use BLE, as explained previously, there will be multiple services, and under each service, multiple characteristics potentially, and then under each characteristic, potentially multiple descriptors. This is a formal API, so to initialize a service, you call getService, and likewise, to get the characteristics, you use what was returned by getService and then call getCharacteristics on that. This is well seen in the code below, where you'll have a call getService on that arg3, and that'll return v0, this object service, and then you can call on that service object v0.getCharacteristic. So for their binary analysis, they can trace back v0 to the service and then create a relationship between a characteristic and a service. More formally said, in the algorithm, they're performing this value set analysis, basically taking an object and going backwards to see where it was used following the code flow. And they'll do that for the descriptors and characteristics, and then able to create a relationship between the characteristic and the descriptor and the service and characteristic. So the output of this whole process is something like the middle tree diagram, where you'll have a device, and then it will have services, and then under each service, the characteristic, and then potentially the descriptors under that. The third challenge that the researchers overcame was identifying vulnerabilities. The researchers stated that a device is vulnerable if it uses the JustWorks pairing method, and that no app-level authentication was used, or that the app-level authentication used was flawed in some way. So the precondition for any of this is that the JustWorks pairing method is used. And so a device mobile app can implement a secure pairing process via a create bond API, or receiving a system broadcast event that carries an action bond state changed. So looking for either this API call or the constant value, they can determine if a secure pairing process was used. If not, they can say that JustWorks was being used. After establishing that precondition, they looked for the absence of cryptographic usage. This was done by looking at various APIs that use the BLE data, just set data but with different parameters, and then tracing back the logic, saying, if it used set value with this BLE data, did that data ever, along the chain of instructions that manipulated that data, did it ever go through a cryptographic function? And those are listed here, doing with encryption and hashing. And if no encryption or hashing is detected, then the app is recognized as vulnerable due to absent crypto. The last thing they looked at was flawed authentication. Specifically, they were looking if there was hard-coded credentials being used. And this was detected similarly by looking at the set value and tracing back the logic of the set value function to see if the data ever could be tied to some input, such as from the network or from the user. If it couldn't be tied back to the network or the user, then it was assumed that it was hard-coded credentials, and thus was labeled as flawed authentication. Having now established the BLE scope, they were able to get into the experimentation phase to start analyzing some apps. So the first step was to actually get an analysis of the Android APKs from the Google Play Store. So there was a data set available that had about 2 million Android APKs from April 2019, but they want to reduce that to just BLE IoT apps. So they applied a heuristic. This heuristic first checked if the app had a manifest file containing rights relating to Bluetooth. So that narrowed the set a bit, and then they could narrow it even further by making sure that the app used specifically BLE-related APIs. Then they found out that some of those apps were just for scanning, so it wouldn't actually be able to communicate with an IoT device. So then they made sure that it had after connection BLE APIs being used. So table 2 shows some of those APIs that they used to filter down to the heuristic. In the end, they ended up with 18,166 BLE IoT apps. Then they were looking at how do we actually gather BLE data from the surrounding area for a nearby attack. They use a BLE sniffer with Raspberry Pi running Linux, connecting with a SIM7000A GPS module, so they could actually pinpoint where they were doing the sniffing, and a special Bluetooth adapter, Pirani UD100, with an amplified patch antenna RP SMA-R/A, which allowed them up to around 1,000 meters of range. Now that the researchers had reduced their dataset of 18,166 BLE IoT apps, they could run BLE scope on it. This took about 96 hours. Looking at table 4, it shows the operations used to resolve UUIDs. And it empirically justifies why, for some apps, you can't just simply extract the UUID as a string. Looking at Table 3 of note, we see the number of UUIDs are often repeated. There are 168,093 UUIDs found, but only 13,566 of them are actually unique. Table 5 shows the mapping between a UUID and an app, seeing that multiple apps are mapped to a single UUID. The reason for this was explained in the paper for several points. First, a company might produce multiple apps that control the same device. They saw this with some HP printers. Separate apps like fitness apps might come from different companies but control the same device. Standard UUIDs can be reused by apps, and unintentionally, sometimes UUIDs are shared between apps. All this leads to a justification why active fingerprinting using the UUIDs found in the hierarchy based on services and characteristics might be useful to further narrow down the connection between a UUID hierarchy and the app, and being able to identify what app is being used.
Another aspect of the mobile app analysis result was vulnerable mobile app identification. Of the 18,166 apps that supported BLE, 61.3% or the majority used the JustWorks pairing. Of these, 15.8% of apps were found vulnerable, with 13.6% having absent cryptographic usage or were considered sniffable, or they had some type of flawed authentication via hard-coded credentials. Another thing of note is that the authors were very generous in terms of their assumptions, and that there might be some false negatives due to the strict rule that flawed authentication simply means data hard-coded. Another point here is the distribution of BLE IoT apps across category. Health and fitness apps make up the most vulnerable apps. So far, the results have identified the vulnerable apps, devices, and their UUID hierarchy. The next question the researchers want to answer is, where are they actually located in the real world? So they were able to sample, using GPS and a BLE sniffer, some data in the area. In their area, they found that 30,862 Bluetooth devices existed. Of these, 5,822, 18.9%, were BLE specific. Of these BLE devices found, 94.6% were fingerprintable. Of these, 7.4% were considered vulnerable, with 6.7% sniffable and 6.2% unauthorized accessible devices. Using the UUIDs, they were able to correspond them to the device's company. So here we have a listing of, like, the top company, Google, had 2,595 devices. In Table 10, we see the top 10 devices found in the field test. This table shows a UUID, a company name, the app it corresponds to, and the number of installs and devices found. Then in Table 11, we see the top 10 vulnerable devices found in the field test, with the highest being a digital thermometer. Following experimentation, the researchers proposed several countermeasures. For mitigating app-level vulnerabilities, they suggest that you should be using cryptographic functions when using the JustWorks method of pairing, as well as remove any hard-coded credentials being used, and instead take input from the user or the cloud. For anti-UUID fingerprinting, they point out that the root cause here is that BLE devices must broadcast advertised packets, and they are fixed values not changing over time. Several solutions are proposed, some with different pros and cons. For app-level protection, you could obfuscate the binary, making it harder to reverse engineer, or add a runtime acquisition of the UUIDs so that analysis could only be performed at runtime or dynamically. In addition, they propose a channel-level protection. There is other work called BLE Guardian, which uses additional hardware equipment that transmit signals that interfere with the sniffing. For protocol level protection, which they offer as the most practical solution, is that you construct a one-time dynamic UID for broadcast communication. This would require software update of both the mobile application and the IoT device firmware. But they said that this can be implemented in less than 500 lines of code, and they have implemented and verified that this works as expected. Basically, you'd still have to have UIDs in the first connection as seen in figure 6, but after that initial connections, dynamic UIDs would be generated. This would be synced between the IoT device and the phone app, and then finally that could be synchronized on the cloud so that you could use it on other apps. As part of this paper, there were several ethical considerations for this project. First, they were never actually able to widely test their hierarchical UIDs for fingerprinting, only testing with their own devices, since that would require connecting to those devices. In addition, they provided a responsible disclosure. They reported the BLE IoT device fingerprinting with static UIDs to the Bluetooth SIG committee. In addition, they reported the vulnerabilities to the developers of the vulnerable apps based on their contact information from Google Play. Overall, and in conclusion, there are four main contributions of this paper. First, they realized that this novel BLE IoT fingerprinting technique. They realized that BLE IoT devices can be directly identified and fingerprinted due to the usage of predetermined static UUIDs in both mobile apps and BLE devices for BLE advertisement. Second, they developed BLE Scope, a binary analysis tool for BLE IoT mobile companion apps. It has two main steps. It extracts UIDs and it detects insecure IoT devices. Third, using BLE Scope, they were able to get some experimental results. They found that 18,166 BLE mobile apps from Google Play Store and found that 168,000 UUIDs, 13,566 unique ones, and 1,757 vulnerable BLE IoT apps. Finally, they presented countermeasures at the app level, channel level, and protocol level.